Mathematics, without a doubt, plays an important role in physics, as the two fields are closely connected. One might describe math as being an important tool for a physicist. Others might argue that their connection goes much deeper. Despite this debate, it is no secret that there are many unique mathematical descriptions used in physics today. Through this video series, we will be exploring one of the most powerful mathematical models to date, called projective geometric algebra, or PGA for short. PGA offers an intuitive model for classical mechanics that can be used to simplify and unify many different areas of math. In this video specifically, we'll be setting up the background and basis for understanding PGA and how it was formed. There exists many representations of the relationship between geometry and algebra. This includes the ancient Greek Euclidean geometry, Hamilton's quaternion algebra, and Grassmann's algebra of extension, among others. During the 19th century, it was a goal in mathematics to construct a unified framework between all the existing representations, but there was one obstacle. Physicists realized that they need to do more than just add vectors. They need to multiply vectors in various ways to solve many of their problems. But creating a suitable product with the elements of a vector space really set the work of mathematicians apart. This unified framework eventually came at the end of the century with the innovations of William Clifford. He introduced a single structure called geometric algebra that is the basis for projective geometric algebra. Geometric algebra focuses on connecting the ideas of linear algebra with geometric interpretations. The geometric algebra of three-dimensional space is a remarkably powerful tool for solving problems in geometry and classical mechanics. It describes vectors, planes, and volumes in a single algebra. One of its most powerful applications is in rotations and other geometric transformations, like reflections and translations. In GA, we use algebraic methods to solve geometric problems, and we use geometric interpretations to help us solve algebraic problems. So for example, the product AB can be thought of as multiplying the sides of a rectangle with sides A and B. In three-dimensional GA, there are three orthonormal basis vectors that are E1, E2, and E3. These are similar to the I hat, J hat, K hat unit vectors that you might be more familiar with. We also have three defined unit bivectors, E12, E23, and E31, made from the products of the three basis vectors. A bivector can be thought of as the parallelogram formed by sweeping one vector along the other vector, so it has an associated orientation with it as well. There is one other element that we have to mention here, and that is the trivector E123, which can be thought of as the cube with each side of the volume being one of the three basis vectors, E1, E2, and E3. Like the bivector, the trivector also has an associated orientation with it. It is important to note here that the order of the subscripts matter. If you were to switch the order of the subscripts, you have to add in a negative sign as they are anti-commutative. So for example, E12 becomes negative E21. And reversing the order of any of the subscripts will also change the orientation of the element. So to recap, we have our grade 0 elements that are the scalars, and these are the set of all real numbers. Our grade 1 elements are the basis vectors, our grade 2 elements are the basis bivectors, and our grade 3 element is our trivector. In dealing with the issue of creating a suitable vector product, the dot and cross product were defined in Hamilton's quaternion algebra. There is one limitation, however, when using the cross product, and that is that the cross product only works in 3 dimensions, and no other number of dimensions. Later, mathematician Hermann Grassmann introduced the interior product, which is the same as the dot product, and the exterior product, which is similar to the cross product, but that it works in any number of dimensions. The interior product, also known as the dot product, takes two vectors and returns a scalar, just like in vector algebra. The best way to think about the inner product is how related the two vectors are to one another. Let's take an example. U and V are vectors, and A, B, C, D, E, and F are coefficients related to the magnitude of the vectors. The first step in this example is to distribute every term. The next step is to realize that the interior product of any two orthogonal vectors is 0, because the interior product is a measure of how similar the vectors are. So when they are perpendicular, they are not at all similar, so this gets a value of 0. and we can now cancel out any of the terms that have the interior product of two different basis vectors, since we know that they are orthogonal. The next step is to realize that the interior product of anything dotted by itself is always 1, because a vector is exactly similar to itself. And on the last line is our result. This is the same result you would get by doing the dot product. You could also represent the interior product in the following way as well, which you might be more familiar with if you've seen the dot product before. This definition is related to the projection of the two vectors. When the angle between the vectors is 90 degrees, the vectors are orthogonal and therefore not related at all. And the cosine of 90 is 0, which shows the same result. And the vectors are parallel, meaning theta is equal to 0 or 180 degrees. The cosine value is 1, meaning that they are maximally similar. Moving on to the exterior product. The exterior product, also known as the wedge product, takes two vectors and returns a bivector, but this can also be applied to larger elements. Looking at the basis vectors e1, e2, and e3, we can form the unit bivectors by using the exterior product. e1 wedge e2 is equal to the bivector e12, which is also equal to negative e21, but it's preferred to write it as e12. The same goes for bivector e23 and e31. Now let's look at an example for the exterior product. So for this example, we are given the same vectors as used in the previous problem. To evaluate, we distribute every element into every other. Note that any basis vector wedged by itself is always 0, so we can cancel out a few terms. We can now change the order so that each of the bivectors are defined as positive. We can group all of the coefficients together, and we get our final result. This is the same pattern as the vector cross product, but generalizes to any number of dimensions. Eventually, William Clifford united both the interior and exterior product as part of his geometric product. The geometric product of vectors includes the interior and exterior product and returns both a scalar and bivector at the same time. Additional terms are added to the geometric product for bivectors and bigger objects. Together, these two measures captures more information that is not present in just the interior or exterior product alone. Let's take a look at another example. We are given the same two vectors u and v that we've had in our previous examples. And from our previous examples, we know the result of the interior and exterior products. So we can just simply plug in the results from the interior product and exterior product into our definition of the geometric product. I'd like to reiterate that the definition I gave for the geometric product of vectors is only valid when you're using vectors. Using what we call the Cayley table for 3D geometric algebra, we can find the geometric product between any of the basis elements. The first row and column are the elements, and the rest of the table is the geometric product between those elements. So for example, say we want to find the geometric product between the bivector e13 and the vector e2. Find e13 on either the first row or first column, and then match it with the corresponding e2 column or row. The result is negative e123 in both cases. This table will help us find the geometric product between any multivectors. So let's take an example. We have two different multivectors, a and b. And the first step is to distribute all of the terms into all of the other terms. Next, we evaluate the geometric product using the Cayley table. Once that's done, we can combine like terms and reorder everything into their preferred form. And this is our final result. We can use the general form of the geometric product to define the interior and exterior products. Let's take a closer look at our example above. In order to show that the geometric product of general multivectors is not equal to the interior plus the exterior product, let's find both the interior product and exterior product and compare it with our results from the previous example. When doing the interior product the same way I showed above, we get the following result. Next, we do the exterior product, and this is our final result. You can see that when you add these two results, they do not equal the result from our previous example. So for general multivectors, the geometric product is not equal to the interior plus exterior product. This is only valid when you're working with vectors. I hope with this that you have begun to consider the importance of using geometric algebra and have a basis for its workings. Thank you for listening.